As you build your DIY data science skills, please do not make the same mistake I did, underestimating the power, the usefulness of k-means clustering. Like many, when I first got started in machine learning, I was obsessed with predictive models, decision trees, support vector machines, neural networks, random forests, you name it. It's not surprising, right? Because predictive models are awesome. Don't get me wrong. They're super, super useful, super, super powerful. But here's the thing. K-means clustering is wildly useful to any professional because the k-means clustering algorithm is specifically designed to mine hidden patterns out of your data where the data doesn't have any labels. And most of the world's data is not labeled. So cluster analysis and k-means in particular is way more useful than I initially thought. So once again, don't repeat the mistake that I made. This crash course will introduce you to cluster analysis using the k-means algorithm. Now there is a little bit of math, just a little bit of math in this crash course, but don't let that scare you away. The math is only at the middle school level. Literally any professional can learn k-means clustering. And I hope that you enjoy this video. I hope you get excited by it, and I hope you start clustering your own data using k-means. Now, if you'd like to follow along, go ahead and get the files. So there's a link down below in the video description. I can send you via email the PDF of all the slides in this crash course, and I can send you a Jupyter notebook of all the Python code. All right, with that out of the way, let's go ahead and get started with what exactly is cluster analysis anyway. So here we have our definition of cluster analysis, and this comes from my favorite textbook on machine learning, which I will recommend to you at the end of the crash course. So first up, cluster analysis groups data objects based on only information found in the data that describes the objects and their relationships. This goes back to what I was just talking about in the intro. Cluster analysis is designed to work with unlabeled data. And let me really cement this for you with an example. So let's say you work in the credit card industry and you want to be able to predict whether or not a credit card authorization is fraudulent. So maybe you're building a predictive model, a machine learning predictive model to do this. So all of your rows of data are your transactions. And then one of those columns has to have an indicator, yes or no, whether or not any individual row, any individual authorization was in fact fraudulent, yes or no. That is known as a label. Cluster analysis is designed to work with data that is unlabeled, which is most data in the world. So moving on, the goal is that the objects within a group be similar or related to one another and different from the objects in other groups. Okay, so what this means is that as we go through with our cluster analysis with k-means, and we go through all of our rows of data and we say, hey, some of these rows go in this cluster and some of these rows go in this cluster, what we want are the rows within the clusters to be very, very similar to each other. And then ideally, the clusters are very, very dissimilar from each other. That is a good clustering. Now, we'll talk more about this throughout the crash course. In the real world, the quality of your clusterings are going to vary. But hypothetically speaking, you have densely tight packed clusters that are far apart. That's the concept. And then next up, we're going to say, look, the greater the similarity or homogeneity within a group and the greater the differences between the groups, the more distinct the clustering or the better it is. Now, because cluster analysis works with data that is unlabeled, it is known as unsupervised learning. Now, the aforementioned predictive model for credit card fraud, that would be known as supervised learning because it used labeled data. Now, because most of the world's data is unlabeled, this makes cluster analysis wildly, wildly useful. And like I said in the intro, this was a big mistake I made. I kind of poo-pooed cluster analysis and yeah, it's interesting, but I'm not going to use it all that much. Turns out that I use cluster analysis quite a bit. It is super, super useful. Now, as I'll talk about towards the end of the crash course, when you combine both supervised and unsupervised learning, that's when things get really, really powerful. So stay tuned for that. Okay. And just so you know, I might use the term group or I might use the term cluster, and they are interchangeable in this crash course. Okay, so that is what cluster analysis is. Let's talk real briefly about why we do it. And the reason why we do cluster analysis is simple. As human beings, we love to group things. We love to classify things. For example, biologists have created a taxonomy for classifying animals, kingdom, phylum, class, so on and so forth. And biologists have been doing this for a long time, zoologists too. And they've spent a lot of time and effort. They spend a lot of time and effort on this because it's super important. But the thing is that these are humans, right? And maybe I'm a zoologist and I go off to some tropical island and I find a new insect and I say it is a beetle. Totally making this up on the fly. So this is a beetle. And then I report my findings back to the community with like an academic paper, and everyone starts shouting me down like, no, Dave, you're crazy. That's not a beetle, it's a fly. I don't know, something like that, right? So human beings simultaneously love to classify things. We love to group or cluster stuff. It helps us understand what the world's going on. But unfortunately, when humans do it, we end up having a lot of subjectivity and bias. So cluster analysis is awesome because not only does it allow us to do this sort of thing, which is what we like to do, right? Group things, classify things, but it also automates it. So it takes the subjectivity and the bias out of it insofar as the actual process. Now, if your data is biased, that's another problem. We're going to go ahead and skip that for this crash course. But in general, the actual process will be unbiased because the computer is doing it. And this also allows us to scale to data that's way larger than what the human brain could actually handle to do this kind of manual classification or clustering process. Not surprisingly, we like to group things in the real world, and that applies in the world of business as well. So here are some examples from my hands-on work, my real-world analytics work, for using cluster analysis in IT, in marketing, segmenting customers, in IT, anomaly detection, text analytics. It's one of my favorite things, actually, is to group documents. I love text analytics. Be a video coming up on that in a while here on my channel. Stay tuned for that. Supply chain, grouping customers, all kinds of stuff. The list just goes on and on and on. Cluster analysis is wildly, wildly useful. Just to expand things, a group, a cluster, and a class are all going to be interchangeable in this course, right? Just like we have kingdom, phylum, and class, that's a way of classifying things. These are also groups or clusters, so they're all synonyms. Cluster analysis is super useful. Hopefully I've sold you on the idea. And moving on now, let's talk about, okay, well, Dave, I buy this idea that we've got to do cluster analysis and that it's useful. What's the big deal? Okay, so here's the challenge. As human beings, we can look at this particular visualization here, and I can say, how many clusters do you see? Most humans, this is a very, very easy problem. Mentally, they will draw something like this. There's actually an idea in terms of visual perception of human beings known as proximity, where we have a tendency as humans, as we recognize patterns visually, to group things based on something known as proximity. So we'll say, hey, all these guys seem to be very close to each other or in proximity, so they kind of seem to be a group. Same thing over here. So we can do this pretty easily as human beings. This is a little tougher for computers to do because they don't actually see technically, right? Where computer vision is getting way better, but generally speaking, they still don't see as well as human beings. So what we can do here is then say, okay, well, this is kind of a challenge, right? A human can do this pretty easy, but how do we get a computer to do it? Now, think about this for a second. Notice here that I'm actually working in a two-dimensional space, right? I have an x-axis and a y-axis. So this is 2 dimensions or 2 features or 2 columns, however you want to think about it, 2 dimensions. And this is pretty easy. Now, I could add a z-axis here and add a 3rd dimension. And depending on how well I rendered that 3-dimensional image on a 2D surface, human beings can still perceive things very well. I mean, we are 3D creatures. We live in a 3D world, so we can perceive clusters in 3 dimensions quite easily. Think about this, right? If a dimension is analogous to a column or a feature in a table of data, how often do you have more than 3 columns of data? All the time, right? And this is where human beings break down. So the challenge is not only do we need to get computers to do this clustering thing in small dimensions where a human can do it quite easily, and we want them to do it as well as we do, but we also need them to be able to scale well beyond what human beings can actually handle, right? 5 dimensions, 20 dimensions, 100 dimensions. So that's the first challenge, right? How do we get computers to perceive clusters as well as we do in lower dimensional space, but also do it very, very well in high dimensional space? Now, the next challenge is your clusters might not necessarily be so simple. So let me go back up a slide. So these clusters are pretty simple, right? Notice how they're kind of spherical, right? These are kind of oval shaped, and you can imagine in 3 dimensions, this would look like an egg. 4 dimensions, it would be known as a hyperegg. Well, the technical name is hypersphere, by the way, but you get the idea, right? These are relatively simple, right? They're spherical, but clusters don't have to be that way. And I've kind of cheated and kind of showed you once again the clusters here by color coding them, just like I color coded the clusters on the last slide. But what we can see here is that once again, in 2-dimensional space, human beings recognize this pretty well, right? Because there's this idea in visual perception of both proximity and continuity. So we have a natural tendency as human beings to see this crescent shape in turquoise here as one grouping, and this coral or orangish color as another grouping. We do this very, very easy. But once again, as we expand the number of dimensions, the number of columns that we're trying to cluster, this gets really, really hard for us. And simultaneously, once again, we want the computer to be able to do this as well with lots of rows of data and lots of columns. So that's the other challenge facing cluster analysis, which is why there are many algorithms, many techniques in cluster analysis that have been constructed, but two of the most useful will be the subject of this video and my next video in this series. All right, so that's a high-level idea of the challenge. Let's really cement what the challenge really is. And once again, this is about the number of data points that we're talking about. So the previous visualizations were created from data sets that look like this, right? A couple of columns, a bunch of rows of data. But in reality, we cluster large amounts of data, thousands of rows, maybe 100 columns, 1,000 columns, who knows, right? Because as we get more and more complicated with our business processes, for example, customer behaviors, for example, we need more and more features, more and more columns to describe things accurately. And that just makes the clustering process more complicated. So that's the challenge. And that's why these algorithms like k-means are so useful, because they actually do this pretty well, generally speaking. All right, so moving on. We can't have a crash course about k-means clustering without having some data. So this is the data that we're going to use in our crash course today. So what we're going to be doing is using the iris dataset. Now, if you're familiar at all with data science and the datasets commonly used in data science, you might be thinking to yourself, oh, Dave, come on, the iris dataset? What's going on? Hang on, just let me explain why. We want to use the iris dataset because it's relatively simple. Because when you're first learning cluster analysis, the last thing that you want to use is a huge complicated data set, because what you're trying to focus on is learning the fundamentals, not necessarily concentrating on edge cases with super hard data sets, because everything that you're going to learn in this crash course applies to way more complicated data sets than what we have here. Hopefully you're still with me. Let me talk about what the data set is, if you're not familiar. All right. So the iris data set is famous. It was created by a statistician in the early 1900s named Fisher. And it is physical measurements of, not surprisingly, iris flowers. That's the name iris dataset. So what we have is a collection of 150 rows, where we have 50 rows of each of three kinds of iris flowers. 1, 2, 3, 50 of each, total of 150 rows. And they are Setosa, Versicolor, and Virginica. Now, each row of data, also known as an observation, is comprised of 5 columns: sepal length, sepal width, petal length, and petal width. Okay, these are the numeric features that describe essentially the physical dimensions of a flower, and they're measured in centimeters here, and you can tell these are numeric. Now, the last row, the last column, the fifth column of data is actually the category. What kind of flower is it? Now, if you're like me, you're not necessarily super familiar with flowers. So let me explain to you what these measurements actually mean in the real world. So here is an image of the iris virginica flower. And what we can do is we can map these columns to the actual physical nature of the flower itself. So this thing here is known as the sepal. I would have called it the flower because I didn't know any better, but apparently this is the sepal. So what we have is the measurement of the length of the sepal in centimeters and the width in centimeters. Now, petal, I'm pretty familiar with petals. Hopefully you are too. So this is a petal, and we also have a measurement of how long they are and how wide they are. Right? So that's the first 4 columns in numeric measurements. Now, maybe your spidey sense has been tingling here for the past few seconds because I said something pretty interesting, which was this data set actually has labels. Is this flower Setosa, Versicolor, or Virginica? So, hey Dave, what gives, man? Why are we working with labeled data in a crash course about k-means cluster analysis, which is all about unlabeled data? And the answer to this is pretty straightforward. Once again, when you're first learning all of this stuff, you want to use a relatively simple data set so that you can focus on the fundamentals. And simultaneously, if you use a labeled data set, this helps you understand what's going on. For example, you can compare the results of the cluster analysis in terms of its quality vis-a-vis the actual real-world data. And this helps you learn the trade-offs. It helps you learn the imperfections in the cluster analysis process. So starting with simple labeled data sets is a great place to start for a crash course. And that's why I'm doing that. Hopefully you're still with me. Now, the cool thing about the iris dataset is that Python gives it to us automatically. Now, specifically, we're going to be using the scikit-learn library from Python. If you're not familiar, scikit-learn is the de facto standard for doing machine learning in Python. It's a whole collection of all different kinds of machine learning algorithms and techniques, including k-means. And it also includes some sample data sets for you to use as well. So in scikit-learn, there is a module, sklearn datasets. And in this data set, there's a function called load underscore iris. This allows us to load, not surprisingly, the iris data set. So we import this in, we get our pandas because we love pandas. Pandas is awesome. We call load underscore iris, call the function, and then we pass in this parameter and say, hey, we want the data as a pandas data frame, please. And then we say, give us the data. And then I'm going to store this in a variable, which I'm calling iris underscore df, iris data frame. And if I call head on it, you can see my data here. And notice I've got the measurements. Now, to level set terminology here, we're going to call our entire data set, all the rows of data, all of the columns, either our data set, a table, or a data frame. Those are all synonymous, very commonly used in machine learning. And along the vertical, we have here, for example, petal width, measured in centimeters. This is known as a column, a feature, a variable, a dimension. I think I've actually used all of those terms already in this crash course, so they're all the same. And then along the horizontal, we have our row or observation, our example, or our sample. These all mean the same thing. It's an item of interest. So when we're doing cluster analysis, our rows have to be our item of interest. Flowers, credit card transactions, patients, customers, insurance claims, whatever it might be. And then, of course, the vertical, the features, the variables, the columns describe each one of those individual items of interest. So that's going to be the data that we're going to be using in this crash course. Once again, everything you're going to learn here using the iris data set as the example applies to any data set that you might think of. Now, with that being said, let's pop up a level and say, okay, we know what cluster analysis is. And you've already mentioned, Dave, that there are many, many ways, there are many, many algorithms, many, many techniques for doing clustering. Let's talk about the various types of clustering that's available to you. And all of these are going to be covered in that textbook I mentioned at the very end of the course. Okay, so first up, we're going to talk about hierarchical clustering. Did I say that correctly? Yeah, hierarchical clustering. So hierarchical clustering takes the assumption that your data is going to be nested. And so for example, cluster 1 contains cluster 5 and cluster 2. Cluster 5 contains cluster 6 and cluster 7. This is a pretty reasonable way to visualize hierarchical clustering at a conceptual level, but it's not necessarily the most intuitive. So here's a better way. Dun, dun, dun. You can visualize hierarchical clustering and hierarchical clusters as a tree. And when most people see this, what they think of first and foremost is an organizational chart, an org chart for your company. Maybe this is the CEO, and this is a VP, and this is a VP, and this is an assistant VP, an assistant VP, assistant VP, assistant VP, so on and so forth, until finally you get at the very bottom, the folks that actually do the work every day. You can think of an organization as being a hierarchy of clusters based on chain of command, based on management. This is a very, very intuitive way to think about it. Now, in general, in hierarchical clustering, there are two ways to come up with this kind of result. First up is what's known as agglomerative clustering, which is a bottoms-up approach. So you take all of your data and you cluster it. And you say, for example, maybe all of my data neatly fits into 4 clusters. Cool. And then you cluster the clusters. And you say, well, these 2 clusters actually belong together, and these 2 clusters belong together. And then you take these 2 clusters, merge them together, so on and so forth. So you work your way from the bottoms up. That's agglomerative clustering. And next up, we have divisive clustering, which is top-down. Now, here's the thing. Hierarchical clustering is something that you read a lot about. It's covered in the textbook that I'll recommend to you at the end of the crash course. However, I will admit, in my real-world work, I have never used hierarchical clustering, ever. Your mileage will vary. You might find it extremely useful. I'm just trying to tell you what it is, and you can always look up in the textbook that I'll recommend how to learn how to do it better if you want to actually use that on your data. Now, generally speaking, remember, you're going to want to use hierarchical clustering in the case where you believe or you need this nested structure. A lot of the times in my experience, what business stakeholders are looking for is not this. They're going to be looking for the next thing that we're talking about, which is partitional clustering. And that is the clustering technique, the clustering algorithm, actually takes the data, clusters it, and assigns each row of data to one and only one cluster. That's partitional clustering. In my experience in real-world business analytics, this is what most business stakeholders want most of the time. They want to be able to say, okay, this is cluster 1. We want to do something to cluster 1 or for cluster 1. This is cluster 2. We want to do something to or for cluster 2, so on and so forth. So this is by far and away, in my experience, the most commonly used clustering technique. And k-means, by the way, preview of coming attractions, is a partitional clustering technique. K-means will find clusters and assign each row of data to one and only one cluster. But that's not all there is. There's also overlapping clusters. Now, overlapping clusters, arguably the most real-world specific kind of clustering technique or clustering algorithm. Because if I go back up a slide, very rarely is the world set up like this, where everything is cleanly delineated between this cluster. I'm in this cluster, but never this cluster, so on and so forth. In the real world, it's a little bit messy, and people tend to be like belonging to multiple clusters simultaneously. So for example, here's a real world example of that type of scenario. So me, Dave Langer, at one time, I was simultaneously a Microsoft employee because I worked at Microsoft. I was a Microsoft shareholder. I had like Microsoft stock in my 401k. And I was also a customer because I had an Xbox Live Gold subscription. So I was all of these three things simultaneously, and overlapping clustering allows for this scenario. For example, the Dave Langer row in the data set might be assigned to cluster 1, cluster 2, and cluster 3 simultaneously in varying proportions. That's usually the way these algorithms work. They take 100% and then they divvy it up. So they might say, hey, Dave is 50% cluster 2, and he is 35% here, and he's 15% here, something like that. Hopefully that adds up to 100%. But you get the idea. As potentially interesting and real world, representing the real world as overlapping clustering can be, once again, in my experience, business stakeholders can't really find this super useful. They don't find it very actionable because they don't know what to do with a row of data where you're 50% here, 35% here, and 15% here. They typically just want each row to be in one thing and one thing only, because then they can assign some sort of treatment or business process change based on that. But I'm covering all this for completeness. Partitional, generally speaking, is the clustering technique you're going to be using probably most of the time, if not all the time. And then lastly, we can combine those three concepts with this idea of complete versus partial. Let's talk about complete. Complete is pretty simple. Complete clustering ensures that every data point is assigned to a cluster. What this means is if you got 10,000 rows, each one of your 10,000 rows of data will be assigned to a cluster. The algorithm, the machine learning technique says, look, I am going to ensure that every piece of data, every row of data is assigned to a cluster no matter what. So for example, we can see right here, this particular data point looks a little bit out of whack compared to the rest of these, but in a complete clustering technique, it would be assigned to this orange cluster because it is the closest cluster for it. On the other side of the equation, we have partial clustering. And this is where your clustering technique, your clustering algorithm says, look, I'm not necessarily going to assign all rows of data to a cluster. So for example, I might say, look, this data point is too far out of whack for the rest of them, so I'm going to leave it unassigned. Partial clustering is super useful in certain circumstances where you don't want to worry about outliers. And I'm going to air quote that, outliers, this idea of something that doesn't look like everything else, like right here. Over here, we have complete clustering. Generally speaking, once again, in my experience, most business stakeholders want complete clustering. They want everything assigned to a cluster, even if it looks a little bit out of whack. So just keep that in the back of your mind. But certain clustering techniques are partial. The next video in my series will talk about a partial clustering technique. So with all that being said, let's talk a little bit once more about the quality of clusters. And I mentioned this in a previous slide. So there's this idea that what we want is our clusters to be well separated. Well-separated clusters are good. Intuitively, we can think of it like this. These are well-separated clusters because there's a bunch of white space right here, right between them. Now, we've already seen a previous example of not well-separated clusters, and this is this right here, okay? So that's the other thing we want to keep in the back of our mind. Whether we're using partial or complete clustering, whether we're using hierarchical, partitional, or overlapping, those things are all details. When we pop up and think about the quality of our clustering more generally, irrespective of those techniques, we want well-separated clusters where we have tightly bound points that are really close together. That's also known as cohesion, right? We want very high cohesion, which means all of our data points are close together and then our clusters are very far apart. That defines really, really good clustering. Now, in the real world, your mileage may vary. Your data may look more like this than it does this, and that's totally okay. With all that said, let's start talking about some more concepts that are super important in understanding clustering techniques. So first up, we're going to have this idea of prototype clusters. Now, prototype clusters is a technique. It's a strategy, if you will, that cluster analysis can take on. And in this particular case, prototype clusters is the idea that what we're going to do is manufacture synthetic data points. And these synthetic data points are going to be our cluster centers. So conceptually, you can see here I've got some data, and these darker data points represent actual rows of data in our data frame. And this big orange dot and this big green dot represent are prototypes. And these orange and green dots in prototype clustering techniques don't exist in the original data set. They're actually manufactured by the algorithm, by the technique, to allow the clustering to work. Preview of coming attractions, k-means clustering uses prototypes. So just keep that in the back of your mind for a later set of slides here. Now, once we set out these prototypes, we can say, look, these are going to be our cluster centers, and then we can assign data points to the prototypes they are closest to. So all of these guys are in the orange cluster, and all these guys are in the green cluster. We'll notice here that once again, I'm just using a two-dimensional representation here just to keep things easy and have it fit on my slide. Every one of these data points here exists at a particular set of XY coordinates, right? Similarly, so do the prototypes. The orange prototype has an XY coordinate, and the green prototype has an XY coordinate. When you use a particular type of calculation to determine where these prototypes exist, they have different kinds of names. So at a high level, all of these things, this strategy are known as prototypes. But for example, if you happen to use the average, also known as the mean, to arrive at the location for your prototypes, then these things are known as centroids. So they are prototypes, but they're a specialized form of a prototype, because when you use the average to find where they belong in the XY plane, as drawn here, but of course in multiple dimensional space, it's the same idea. These are known as centroids because we're using the mean, the average, to calculate them. Okay. Now, that's not the only calculation you can use. For example, you can also use the median to try and to calculate the XY coordinates for these guys. And these would then be known as medioids, not centroids. Medioids and centroids both are prototypes, but not every prototype necessarily is a centroid or a medioid. Yeah, that's exactly correct. When you use centroids, which is very, very common, by the way, using the average is a very common thing to use in clustering techniques. The clusters that are found are these spherical shapes. So if you're using prototypes and you're using centroids, generally speaking, you're going to find these spherical clusters. Okay, keep that in mind. Preview of coming attractions. K-means, this is where the mean comes from. It uses the mean to center the prototypes. So k-means is a centroid-based clustering technique. Okay, keep that in the back of your mind for later slides. Next up, we can say, look, well, maybe we don't want to use prototypes. Maybe we've got a situation where creating spherical clusters like this is not a good idea. So we need a different technique. We need a different strategy for clustering. And that's where density-based clusters come into play. Now, the subject of my next video will be dbScan, the dbScan algorithm. dbScan is a density-based clustering technique. So density-based clusters are essentially built by looking at your data and figuring out where do you have areas of lots and lots of data points, high density, and where do you have areas of low density, no data points, or very, very few data points. And then what you say is, well, high density with low density in the middle, that's one cluster, that's another cluster. So visually, using this previous example, we can see that sure enough, this is obviously high density here, this is high density here, and this is low density in the middle. So density-based clusters can find these very complicated irregular shapes. That is, when your data has clusters that are not spherical, generally speaking, density-based techniques are going to perform better. They're going to give you better results. So this is a great example, right? This crescent moon shape and this crescent moon shape. Using a centroid-based approach, you're not going to find two clusters because you cannot draw an oval that exclusively has only orange dots or turquoise dots. So it just doesn't work very well. You can certainly apply it to your data, but it's not really going to work all that well. Inevitably, when I teach this stuff live, people ask me, Dave, how do I know what situation my data's in? And the answer is, you can't know, not really. If you have thousands of rows of data and you have dozens of columns or 100 columns, there's no way for you to really figure this out. And don't panic. This is actually a good thing because this is job security for you. Because what you do, and this is very typical in real-world data science, is you apply multiple clustering techniques and then evaluate the quality of the clusters. And then you say, hey, I used a prototype centroid approach and it didn't work very well. So I'm going to use a density-based approach. Hey, that worked pretty well. Or maybe the opposite's true. So it's typical to try out a couple different techniques at base. My classic is to use k-means, the subject of this video, and then dbScan, the subject of my next video, and then compare the results. And if one of them works well enough, is useful in terms of its results, I'm good to go. Sometimes Both are actually useful, which is pretty cool because then you can like blend the results and get a little bit better insight into your data. Sometimes neither one will work. And then either you might have to go find another algorithm or potentially your data just doesn't really have very good clusters. That's always possible as well. But you never know until you try. So job security, yay. When we're evaluating the quality of our clustering, I've kind of hinted to what we're really thinking about here, right? So we're going to be talking about cohesion and separation. I've already mentioned that, but we're going to represent these things graphically because it makes it really, really easy to understand. As I mentioned before, when we have high cohesion, that means the distances between the data points and the cluster center is small if we use a centroid-based approach, which is the easiest way to think about it. But conceptually, it works similarly with a density-based, right? You know, what's the average distance between the data points, for example, in one of those crescent moon shapes? Same idea. So we're just going to use centroid-based approach to really cement this idea. So cohesion are these little distances between all my data points and my cluster center. Now, conceptually, separation is not too difficult of a concept, right? If I have two clusters, I want this distance between these two centroids to be as far apart as possible. As it turns out, when you think about clustering generally speaking, but certainly in the case of k-means, the k-means algorithm, there's this conceptual relationship. In general, it's not a certitude, but in general, as your cohesion improves, that is the distances between the data points and the cluster center get smaller, the separation between clusters gets larger. And k-means uses this relationship to try and find the optimal way to cluster your data. One of the easiest ways to understand this conceptual relationship is to think about the most absurd case possible. Because notice here I have 1, 2, 3, 4, 5, 6, 7, 8. Did I count that right? Yeah, 8, 12, 15 data points, if I count that correctly. So I have 15 individual data points, these little blue guys here. And then I said, hey, I want to find 2 clusters. And I got my cohesion and my separation. Now imagine, if you will, I had 15 data points and I said, I want to find 15 clusters. Okay, this is absurd. Okay, so just roll with it. I have 15 data points and I want to find 15 clusters. So what ends up happening is each one of the data points becomes its own cluster. And if you think about that in the extreme, what's the cohesion? 0, right? If every data point is its own cluster, then the distance between each data point and its cluster center is 0. And then separation is maximized in aggregate because everyone's its own cluster. So that's the way to think about it. I mean, it's absurd. You would never do that in the real world, right? Because it doesn't really give you a lot of information, useful information. But it's a great mental exercise to understand this relationship. That's enough background. Let's talk about k-means itself. Let's put everything together. The k-means algorithm is a prototype-based complete partitioning clustering technique. Whew, that was a mouthful. But now you know what it means. No pun intended. Now you know what it means. It's prototype-based, right? It uses prototypes. In particular, it's using means to find the positions for the prototype. So it is a centroid-based algorithm. It's complete. Every row of data will be assigned to one cluster. And it's partitioning, which means that only one cluster. It uses centroids. Every row of data gets assigned to a cluster, and every row of data gets assigned to one and only one cluster. So here's that all written down for you. If you decide to get the files, of course, you'll get the PDF of the slides, and that'll be in there. Okay. Now, k-means, okay, this is a bit of a lie, I gotta admit, right here. So I say in the slide here that k-means is one of the most popular clustering techniques. That's not true. It is by far and away the most popular clustering technique used in real-world business analytics. And the reason for this is twofold. First up is the algorithm's simplicity. It's really easy to understand how k-means works. And I'll talk more about that in a few slides. So that's the first thing. It's really easy to understand how it works. 2, it works surprisingly well in most circumstances because most real-world business data ends up having these spherical clusters. So k-means tends to work really, really well in many, many situations. Easy to understand, easy to use, and it's effective. No wonder it's so popular. Okay, so let's talk about the k-means algorithm. So here's a definition of an algorithm. I won't drain it for you. You can certainly pause the video if you'd like and read it. The easiest way to think about it is an algorithm is like a recipe. It's a way for taking your raw inputs, doing something to it, and then producing some sort of output. So here's the k-means algorithm step by step. Here's the recipe. So you select k points as the initial cluster centroids. K means the number of clusters to find. You then form those clusters. You then recompute. So what you do is you actually say, okay, all of these data points belong in this cluster, all these data points belong in this cluster. Then I move the clusters to be in the center of the cloud, right? The cloud of data points. And we use the mean to do that. That's where k-means comes from. And then what we do is, as long as the clusters are still moving, right? Because after we move the clusters, we then have to go check all the data points again, see if they belong to the right cluster. And then we move and check and move and check and move and check. And we keep doing that over and over again until the cluster centers do not change. Once they do not change, you're done. Now, that's a bit abstract. I'm going to show you how this actually works step by step in slideware. Once again, k-means is super simple. I can actually explain the algorithm to you using slideware. A couple things that we need to talk about before I run through the slideware is this. The first step in k-means is that you have to pick k. You, as the data analyst, the DIY data scientist, have to tell k-means up front how many clusters to find. 2, 3, 4, whatever it might be. As it turns out, picking the right or the optimal value for k is not easy. It's a non-trivial problem. The good news is that the textbook that I'll recommend to you at the end of the crash course has more coverage about how to do this. Can't cover it in this crash course, just way too much material. To the slideware. So here's our hypothetical example. So if I show you this data and say, look, I'm going to use this data to run you through the k-means algorithm, a couple things are going to pop into your mind. First step, you're going to say, look, these are some obvious clusters here, Dave. This is obviously a cluster. This is obviously a cluster. My eyes do not lie to me. And this particular data point looks like it doesn't, it's kind of an outlier. Now, I'm going to call this outlier Taylor Swift or T-Swift. I'm wearing a Judas Priest t-shirt right now, so obviously I'm not a Taylor Swift fan. But I know enough about the music industry to know that Taylor Swift is an outlier. Okay, so this is T-Swift here, Taylor Swift. In this contrived example, we're going to assume that we've been told by our subject matter experts that k should be 2. Now, you might think this is completely contrived and arbitrary, but I've actually had this happen to me before in the real world. Sometimes your subject matter experts tell you, we know there are 4 segments in our customers, so go find which of the 4 segments our customers belong into. So it's not as far-fetched as you might think. The book that I'll recommend to you, the textbook I'll recommend to you, will provide you other ways to use the data itself to try and find an optimal value of k. But for this contrived example, we're going to assume we've been told that we need to find 2 clusters. Here we go. So first up, k-means is a prototype-based clustering technique. So it needs some place to start the process. It needs to put those prototypes out into the space somewhere. Typically what it does is it tries it at random. So literally what it does is it says, I'm going to throw out 2 data points, 2 prototypes at random into the space, and then just run through the algorithm. And let's assume that we land like this. So we throw out 2 of our centroids here, centroid 0 and centroid 1, and we start running through the algorithm. And the algorithm is super simple conceptually, right? So the first thing we do is we say, okay, cool. We go through every data point and we calculate the distance from each data point to each centroid. In this case, we have 2 centroids, but the process would work the same if we had 3, 4, 5. It doesn't really matter, okay? So we say, what's the distance here to here? 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 And we do that for every single data point. And then we say, okay, for each individual data point, each individual row of data, assign it to belong to the centroid or the cluster center that it is closest to. So not surprisingly, all of these guys are closest to centroid 0. So they're all part of the orange cluster. And then we do the same thing, and what we find is that all these guys are obviously closest to the green centroid here, but T-Swift, actually right now, it's really, really, really tight, but she's actually closest to the green centroid. So T-Swift, Taylor Swift, gets assigned to centroid 1, the green cluster. And we say, okay, cool. Now we got a problem. So I've color-coded the dots here based on their assignment. These are all orange, these are all green, including T-Swift here. Now we'll notice that our orange centroid here and our green centroid here are not actually in the centers of the clusters, are they? This guy is nowhere near the center of the cluster because it's probably like somewhere like right here. So the algorithm needs to move the clusters. And this is where, like I said, where the k-means comes from, because we actually use the mean or the average of the cluster's data points to calculate where the centroid needs to move to be in the center. So using our graphic here, we take the average of all the x values of all these orange data points, and then we take the average of all the y values of these data points, and that provides the destination. That provides the exact place that the orange centroid needs to move to. So boop, boop, boop. Boop's a technical term, by the way. Machine learning. And then we say, okay, cool. We've moved the orange to the center of the orange data points using the average as our calculation, the mean. And then we do the same thing for the green. And boop, boop, boop. Now, what's super interesting is, check this out. I mean, if we think about it, let's go back up. Boop, boop, boop. This green centroid doesn't look like it's in the center of these green points, right? And the reason for that is because of T-Swift. Because the k-mean algorithm is complete, it means that even outliers like T-Swift have to be assigned to a cluster. And because we use the average to determine where the cluster center goes, it is sensitive to outliers. So T-Swift effectively pulls the green centroid further left and further up than the actual mass of points here, right? Because she's actually exerting a lot more influence on the average or the mean calculation. So that's super important. K-means is sensitive to individual outliers. It will affect your clustering results. But once again, generally speaking, in the real world business analytics space, K-means is remarkably effective. So we tend to deal with this quite a bit. K-means is an iterative algorithm. Okay, that's just a fancy way of saying that this process that I just walked you through gets repeated over and over again until a stopping condition is reached. Now, once again, we want to make sure that we're looking at T-Swift to see what's going on. The cycle just repeats all over again. We go through every data point, calculate the distances, and then assign things appropriately. Now, check this out. Notice that T-Swift is now actually closer to the orange centroid than she is to the green centroid. So on this particular iteration, this particular loop of the k-means clustering algorithm, we now assign her to the orange. And because of that, we need to move the centroids again. So once again, we just calculate the averages and then boop, 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 boop. The algorithm does another turn of the crank. It says, okay, cool. I'm going to go through every data point, calculate the distances, and then I'm going to use the average again and then check the centroids. If the centroids don't move, which they won't now, right? Because everybody's all assigned to the right cluster center, the centroids won't move, and therefore the algorithm stops, and there your clusters have been created. So that's it. That's k-means in a nutshell. This algorithm is super simple. By the way, these slides actually come from years ago when I actually built them to teach my business stakeholders how k-means worked. I don't advise you doing this, but I did it because they were they had a little bit of trepidation about using cluster analysis, right? Because they wanted to understand how it was going to come up with the results that it did. So I walked them through the algorithm. Super simple. They were totally cool. I went off and did the cluster analysis and things were awesome. Okay. So that's the k-means algorithm. Not surprisingly, one of the most important things for the k-means algorithm is to define distance, or more generally, how does it define what is close? Because if you don't have a way of calculating distance and closeness, the k-means algorithm doesn't work. So here's where the math comes in, and it's middle school level, like I said. Okay, it's not super difficult. So by default, k-means uses a calculation known as Euclidian distance, and that sounds really fancy, right? This is a shock and awe term that you tell your manager, right? I learned about Euclidean distance today, boss. And they're like, whoa, that's totally cool. But here's the easiest way to think about it. Back in middle school, or maybe even elementary school, depending on how you were taught, you learned about geometry. And you were taught something called the Pythagorean theorem. Pythagoras was a famous Greek science mathematician guy, okay? And he realized that there was a relationship between the lengths of the sides of a triangle, specifically a right triangle. And a right triangle has a 90-degree angle, if you don't remember, okay? And generally speaking, the Pythagorean theorem is taught this way, right? Where we have a side called A, a side called B, and a side called C. Typically the long side, which is also known as the hypotenuse, is called C, the long side here. And the specific mathematical relationships between these sides of the triangle is A squared plus B squared equals C squared. Or alternatively, with a little algebra, C is equal to the square root of A squared plus B squared. This is the secret sauce of how k-means finds the distances between data points and centroids and defines what is close. So let me expand on this a little bit. So we can also think of A, B, and C like this. So imagine, if you will, that this is my data point, right here. At this point of the triangle, this is my data point. And this is my centroid, the current centroid that I'm looking at. And I want to find C, the distance between this particular data point and this particular centroid. So I can think of it in terms of X and Y's, right? So along my X-axis, the length of A is actually X2 minus X1, right? So let's say this is 7 and this is 4, right? So 7 minus 4 is 3. That's the length of this side. B is Y2 minus Y1. And it's possible that you might get a negative number here. That's totally okay, because remember, we're squaring everything, right? Totally cool. So if we plug and chug, we can say, okay, a squared plus b squared equals c squared, c equals the square root, but b is equal to this, so we'll put this here, we'll put a equals to this here, we square them, so even if the numbers are negative, it still all works out just fine. And then we can calculate the distance between this data point and the centroid. That's how Euclidean distance works in 2 dimensions. Now, here's the thing. Euclidean distance, or the Pythagorean theorem, scales. So if I added a 3rd dimension, like a z-axis here, I would just add another squared term plus z2 minus z1. And this keeps going. I can put in 4 dimensions, 5 dimensions, 27 dimensions, 1,000 dimensions. So it scales to the number of columns that you have. So Euclidean distance is really super powerful. Okay. Now, if you get the textbook and read it more about cluster analysis, you'll find out that Euclidean distance doesn't work as well when you have lots and lots of columns, lots and lots of dimensions. But in general, it works pretty well. Now that you know all of the high-level stuff, how do you actually get this to work? So it's time for some Python code. So here's k-means with Python. So first up, I'm going to load the data set. We saw this already. Saw this code already. And by the way, you'll get all this code if you opt for it. I can email it to you as a Jupyter notebook. We then say, cool, let's go ahead and start doing our k-means. So what I'm going to do here is I'm going to go to scikit-learn, which is the de facto machine learning library in Python. And I'm going to go to the cluster module and import the k-means class. The k-means class, not surprisingly, implements the k-means clustering algorithm. And I can instantiate a k-means object. Now, when I instantiate a k-means object, I need to provide it the information of how I want it to do the clustering. So first up, since I'm using the Iris dataset, I know for a fact that there are in fact 3 clusters. And I'm only doing this to, once again, show you the differences between the actual data and the clustering results, right? So it's the trade-off it's how you learn how the algorithms work. So I got 3 clusters here, and in underscore init is the number of random starts that I would like it to try. Now remember, k-means has to toss out those centroids at the very beginning of the algorithm. Now, the problem is that you could toss out some centroids, and they might, at random, just end up in bad places. And the clustering that you get as a result, it stinks. It sucks. So what you can do is you can tell the algorithm to try it multiple times. So toss out 3 clusters, see how good is it? Toss out 3 clusters, do it again, do it again, do it again, do it again, do it 25 times, do 25 iterations of the entire clustering process, and then return me back the best one. And the one that you get back is the one with the best cohesion score, essentially, right? Because remember that relationship. The better the cohesion, the lower the cohesion score, generally speaking, the better the separation. So it'll try 25 times at random, and it will return you the one with the best cohesion. Okay, so best total cohesion across all the data points, by the way. Okay, now because k-means is a random algorithm, if you want to see the same thing, if I want you to see the same thing that I'm showing you on my slides, I have to make sure that we both start the randomness at the same place. Okay, randomness. That's what this thing does here. Random state, 5, 4, 3, 2, 1, totally arbitrary number. This just ensures that you will see the same thing that I do. So generally speaking, we use the random state only when we need reproducibility. Like if you want to share your Jupyter notebook with a coworker and you want them to see exactly the same thing that you do when they run the code cells, you got to set the random state. Otherwise, don't worry about it. I get back my object, which I call k_means. Not a bad name. And then I call fit on it. In scikit-learn, fit follows a naming convention that says go learn from the data. Essentially, that's what this means. Go learn from the data, k-means, based on the stuff I put up here. Now, to make sure that everything fits easily on my slides, I'm only going to cluster in 2 dimensions, even though there are 4 dimensions in the Iris dataset, or 4 columns. Right? I'm only going to use 2, but you could certainly use all 4. And conceptually, everything that you've learned works. It just, you can't really see it very well in slides for obvious reasons. Okay, so what I'm going to do is I'm going to say, hey, go ahead and cluster my iris data set, right? Which I'm calling iris underscore capital X. That's another naming convention for scikit-learn. These are my columns that I want to cluster, capital X. And of those, I just want you to use these two, petal length and petal width. That's it. Okay. And then this line of code actually goes off and does the work. So it does the entire clustering process a total of 25 times, each time finding 3 clusters, and it returns me back the single best run of k-means based on the best cohesion. And then once I've done that, I can access my k-means object to get the labels. And these are the actual cluster assignments. Okay. And all I'm doing here is grabbing the cluster assignments and then adding them back to my original data frame here. So that would be the first row belongs to cluster 0. The second row belongs to cluster 2. The third row belongs to cluster 1, so on and so forth. And now I can call value counts on this, and you can see here that I have 3 cluster assignments, right? Because I had 3 clusters. And because it's Python, it starts counting from 0. So I have cluster 0, cluster 1, cluster 2, and we can see the counts. So 52 of the 150 rows belong to cluster 0, 50 belong to 1, and 48 belong to 2. Okay, now here's the thing. This is super, super important. K-means doesn't understand anything about your data. It doesn't know that this is iris flower data. It doesn't know about patients or credit card transactions or insurance claims or customers or anything like that at all. It just knows that this row of data is in this cluster. This row of data is in that cluster. That's all it knows. It's up to you as a DIY data scientist to actually crack open the cluster assignments, analyze them, and try and derive business meaning from the clusters. And we're going to talk more about this at the very end of the course when we talk about cluster interpretation. But in general, here's our cluster assignments. Okay, now that we've got cluster assignments, since we're using labeled data, we can now visualize the cluster assignments and then compare them to the actual labels. So I'm going to use the mighty plot9 here. This is my favorite data visualization library in Python. I actually have a crash course video on plot9. If you're not familiar, I'll go ahead and put a card to that up here. And I'm importing from plot9 some functions here. And what this allows me to do is then create a dot chart, also known as a scatter plot, where I'm plotting along the x-axis my petal length in centimeters and my petal width in the y-axis. And then I'm using this thing here to actually just make my chart, my visualization just black and white, theme BW, black and white, nice and clean. And then I'm going to color code each of the dots based on the label, the cluster assignment. Okay. So if you run all this code, this is what you get. Right? So you can see my cluster assignments here are represented by colors, 0, 1, and 2. If I didn't do this factor thing, it would treat my labels as numbers and it would look completely different. So I need to make sure that it says, look, no, the labels, even though they're numbers, they're actually categories. So category 0, category 1, category 2, color code appropriately, please. And what we can see here is that k-means correctly found that there's a spherical cluster down here. Great. That's nice, right? Human being would see that right away. Now things get a bit more complicated up here. And it says, look, I think this is one cluster, and I think this is one cluster, okay? And we can look at this and say, okay, it's kind of reasonable. We told k-means that it has to find 3 clusters, and it will. It will always find the number of clusters you tell it to, no matter what. So given the fact that this is a big blob, this looks like a reasonable split, all things considered. Now, this is where using labeled data becomes really, really super useful because we can compare this visualization to the actual data labels to see how well the clustering worked. So here's the code for that. And all I'm doing here is pulling from my iris underscore bunch. This is the object that I get back that has my data. And I just say pull the original labels, which I'm calling iris underscore y here. And all this code looks pretty much the same. And it produces a couple of visualizations like so. Okay. And what we can see here are the k-means clusters. And over here are the actual clusters. And what we notice here is there's a little bit of difference. Now notice that the color schemes are not exactly the same, but notice there's a cluster down here, and this big blob is actually separated by 2 clusters. And what we can see here is that there are a couple of errors, essentially. Actually, a few errors. So notice that this dot here doesn't belong to the right cluster compared to this dot here. This dot here doesn't belong to the right cluster compared to this dot here. These 2 dots don't belong to the right cluster. right? So we got about, looks like four, maybe 5 errors that I can see off the top of my head. But this is really super important. This is super important. This is why we use labeled data when we're first learning cluster analysis with k-means, because we can start to understand that clustering is never perfect. It's an approximation. It's a model. All models are wrong, but some models are useful. And what we can see here is that the k-means clustering of our data is not 100% correct vis-a-vis the actual labels, but it's pretty good. And what that tells you is that in general, once you move into the real world where you have unlabeled data, if you get good at using k-means, you'll probably get decent results. You'll find insights in your data, if there are insights to be found. As I mentioned, sometimes your data just can't be clustered very well at all, and that's just a function of the actual data, but you'll never know until you try. Okay, so all that said, let's make sure that we're crystal clear on the k-means caveats. Okay, k-means is by far and away the world's most popular clustering algorithm for real-world business analytics, but it's not without its problems. First up, you've got to choose the value of k. That's a non-trivial problem. So there's a couple of ways that you can do that. One is you can rely on subject matter expertise, right? Maybe you have business subject matter experts and they know, hey, we've got 4 customer segments. We've always had 4 customer segments. K equals 4. You can also use what's known as a scree plot elbow method to try and find from the data an optimal value of k. And you can also use something as the average silhouette score. Now, in general, here's what I will tell you. In my experience, if you have subject matter experts that tell you the value of k, certainly use that value of k. I don't want you to get fired. But also use these others techniques, just to validate that maybe, in fact, the prevailing wisdom is not correct. So, and the textbook I'll recommend will teach you about these techniques. Now, in general, given the random starting points, k-means is non-deterministic, because if you don't set the random state, you'll get different results every single time. Okay. Now, because of this non-deterministic thing, it's best practice to run k-means multiple times. That was the n_init thing that parameter that I set to 25 that I showed you in the code. Question I commonly get, hey Dave, how big of a value should I set n_init? And my answer always is as big as you can stand. Because the higher that value, the longer the code takes to run. So if you have a really, really big data set, you wouldn't want to set it to 1,000 because it would take forever to run. So generally speaking, 20, 25-ish, if you can. More is better than less, of course, but as long as you can take for the code to run, is generally speaking the qualitative answer. Okay, and then once again, if you need reproducibility, set the random seed. Okay, so another caveat of k-means is that it only works with Euclidean distance. And let me back up. By default, k-means typically uses Euclidean distance. Euclidean distance only works with numeric data. It doesn't work with categorical data. Some resources at the end of the crash course will help you in the situation if you actually have categorical data that you would like to include in your k-means cluster analysis, okay? But technically speaking, most of the distance calculations, including Euclidean distance, commonly used with k-means, do not work with categorical data. All right. And then lastly, we talked about this before, which is because k-means uses centroids, it creates spherical clusters. And that works great as long as your clusters in your data are naturally spherical. If they're like those crescent moon shapes that we saw earlier, k-means probably isn't going to work. So you might want something like dbScan, which will be the next video in my series, instead. Let's talk about interpreting clusters. This will be the last subject of this particular crash course. Here is one of the most powerful techniques that I mentioned earlier for interpreting your clusters, and that's using machine learning. Is using a machine learning predictive model to help you understand what's going on in your data. So here's an example. Not using the IRIS dataset, using a different dataset. This dataset is what is known as the heart dataset. Essentially, it has rows of data where each row is a patient, and then there is a column, a label of whether or not they have heart disease. And I'm just using this as an example. And what we've done here is we've asked it to create clustering of people that don't have heart disease and do have heart disease. And then what we can do is then say, once we get those cluster labels, we can actually build a decision tree model, a random forest model, an XGBoost model to say, hey, look, I've got my cluster assignments. Go learn how to predict the cluster assignments from the original data. And then once you get that model back, you can actually then use that model to help you interpret the clusters. So let's talk about how this works using a decision tree, because a decision tree is usually a really powerful way of doing this if you can get away with it, because decision trees are very easy to understand. They're very easy to interpret. So I've used this technique tons of times in my career. Cluster data using k-means, and then I'll build a decision tree to actually interpret the data, and then I can use the decision tree to explain the clusters to my stakeholders, either directly showing them the tree or just summarizing the tree in slides. Okay, so the first thing we need to know about decision trees is everything to the left is a yes, and everything to the right is a no. So for example, notice that the first thing that this decision tree found about the cluster assignment is it looked at maximum heart rate. And it said, look, every patient whose max heart rate was less than or equal to 150.5 goes over here. So if their max heart rate is lower than this, then they're in this particular category. And if everybody who has a max heart rate higher than that, like using a treadmill test, they go over here. So that's pretty good interpretation, right? Because generally speaking, your max heart rate is highly associated with your general level of health and also your age, typically. Okay, those two things are related. So this is a very good thing. Okay, cool. And then let's say we're going to go over to this side, just for the sake of it. So the next thing we look at is, these are all the various features. Fluoroscopy, I don't even know what that is. If your fluoroscopy is less than or equal to 1.5, you're over here. Otherwise, you're over here. But what we want to see here is also this idea of the rows of data. Because up here, we have 270 rows of data in our entire data set, and 148 of the 270 flowed down here. So 148, more than half of our data, had max heart rates greater than 150.5. Okay, so that's our first level of interpretation for people over here, right? And then we can say more than half, and then we can just keep interpreting, and we say, okay, let's say, for example, for folks that have fluoroscopies, hopefully I'm pronouncing that correctly, less or equal to 1.5, they go here, we check for angina, and if you don't know what angina is, it's a heart condition, and we say, okay, folks that do not have angina go here, folks that do have angina go here, and then what we can see is we can look at this little last part of the decision tree, and what this decision tree says, we predict that they're in cluster 0. So notice that a lot of people end up in cluster 0 here. And how we can do that is we can interpret this particular assignment by saying they are people with max heart rates greater than 150.5, fluoroscopies less than or equal to 1.5, they do have angina, and they're in cluster 0. So that's one way to characterize the folks that end up in cluster 0. Over here, we could do the same thing. So these are folks that have max heart rate less than or equal to 150. Their old peak is greater than 0.85, and their blood pressure is greater than 102. And they end up in this particular cluster, right? Which is cluster 1, overwhelmingly. Now, this is super, super awesome. So if you're interested in learning more about decision trees, which is a way to interpret your clustering, I do have a crash course on my YouTube channel. I'll put a card up here, and you can check that out and learn more about decision trees, and then you can combine the two. They're like chocolate and peanut butter, better together. To wrap up this crash course, here are some resources to continue your learning. So this is a free book. You can Google it, download the PDF. It's a very high-level introduction. It covers lots of different techniques. It covers decision trees and k-means clustering and all kinds of good stuff. Great book. It's free. However, if you're serious about cluster analysis, this is still my favorite book. You can see here I took a picture of it on my dining room table. This was the textbook that I first used in my master's program in computer science to learn about machine learning and clustering. This is a great book. So good. You can get it on Amazon. I think it's the second or third edition out now. This book is not very mathematical. It does have some math in it, but just enough, not too much. And it's not actually in Python. It's actually language independent, technology independent, which is great because it really focuses on teaching you the concepts. And there's so much good stuff in this book. It's so, so good. So if you're interested in a good book on cluster analysis, covers hierarchical, DB-scan, k-means, right? All kinds of good stuff. This is a great, great book you can get. Okay, there you have it. So hope you enjoyed this crash course. If you're interested in learning more, be sure to check out the description below. for more resources that I have on my YouTube channel. And also, if you're interested in online courses, if that's the way you roll, you can also get a 20% discount on my machine learning online courses in the description down below. Next up in my series, as I mentioned, there is going to be a crash course on dbScan, which is a density-based clustering technique, which is super, super useful. When that video is ready, it'll show up here on the screen as a tile. And until then, I'll put up my decision tree crash course, so you can watch that if you're interested. Okay, so that's it for this video. Until next time, please stay healthy, and I wish you very happy data sleuthing.